Hello. So this is a part 3 of my introduction into the subject which I'm calling the motivation for copulas and their usage in estimating the joint distribution. In the part 1 we spoke about joint distribution, where they come from. Then we looked at this histogram or frequency table method of estimating joint probability density functions, and then we've learned that when we get more granular grid to build this PDF, it seems, not seems, but it's clearly increases the noise in each of in the PDF. So if you want more granular PDF, you build a more granular grid, like more detailed grid. Then each cell in the grid will get more and more noise. And why? Because when you're increasing the number of cells but your sample size is still the same, per cell there's fewer and fewer observations, right? So if you have just one observation in the cell, and then let's say you tried another sample, easily that observation could become zero. Maybe in next sample there will be nothing in that cell. On the other hand, if your grid is very coarse, maybe it's more stable, but then it's not detailed enough. So we seem to have this conundrum. And then in part 2 we looked at how exactly in this method how we would go about estimating density function from the frequencies, and how we build these frequency tables and so on in Excel. I showed you those examples. Now part 3, we are going to talk about the uncertainty in this method of density estimation. What is uncertainty about these numbers, which are the density function, right? Let's start with that. So we will look at any cell. So in this case we have a grid 8 by 8, right? And I'm going to introduce some notation. I'm going to say M is equal to 8. M is the granularity of your grid. It's how many steps or how many cells along an axis in the grid you have. So if it's M is 8, then it's 8 by 8 grid, right? Delta W and delta H are ranges of weight and height. So my weight goes from 40 to 120, so its range is 80, and my height goes from 140 to 260 centimeters. N is 507 observations. So now I'm going to denote FWH is a true density function. So let's say there is a true density function. We don't know it. We're not pretending we know it, but we're trying to estimate it, right? So how do we estimate this this density function? Well, we do the following. We start with actually with probabilities, right? So this is our so the question I'm asking is, what is the probability that the number of observations in any grid would be n, let's say I. So maybe let's say in the first grid is 1, right? So ni would be equal to 1, and I is a number of a cell. So in this case I would run from 1 to 64, right? We have 8 by 8, 64 cells. What is the probability, what is the average number, sorry, not probability, but what is the average number of these observations? And we will say it's Pn, so some probability that the adult in the sample belongs to this cell, and multiplied by the number, the size of the sample, number of people in the sample. And what is this probability? Well, the probability is the density multiplied by the area of this little cell, right? And area is going to be height and weight. So in this case weight is 40 to 50, which is 10 kilogram, and height is going to be 140 to 147 and 5, so 7 and 5 centimeters, right? And that's going to be here. So here I'm using M, which is 8, and then I'm using delta W and delta H, their ranges. So that would be the probability. Now, I already said it several times, and we should be clear about it, that the number of observations in each cell is going to be different with every sample, right? So it's a random number. If it's a random number, we always ask a question of what is its distribution. So if you think about it, you have a probability of p, a person will fall into the cell, and n minus p will not. And that's all. And then you have n people. So ni must be how many people actually fall into this cell or belong to this cell, and that must be binomial distribution, right? It's n successive independent Bernoulli trials, right? In the cell, belongs to the cell, does not belong. So it's a binomial distribution with the following parameters, and we know basically all the parameters. We'll assume that we know p, but we obviously don't because we don't know the true distribution. And we're trying to estimate it actually, right? But you'll see that it won't be that important here. So since we know the binomial distribution, it's very easy to calculate its expected and value and variance. It happens to be Pn, the expected number, average number, and that matches our first step, right? But the variance is interesting. This formula, that's variance of binomial distribution. You can check it in the internet somewhere in Wikipedia or your favorite textbook. Now, knowing the variance and the average, we can calculate the measure of uncertainty. Let's call it a relative error or noise. What is it going to be? It's going to be standard deviation of this number of people in a cell over the average number of people in a cell. So we'll plug the formula, we get this square root 1 minus p over pn. It's quite often, you can see this kind of expression, let's say in Monte Carlo simulations, right? When you are estimating the precision of your Monte Carlo simulations. So you can see this kind of expression quite often. But then we can simplify further. So usually p is low, the probability is low, so I will just replace it with 1 and get this following expression. Now I'm going to make a further rearrangement, right? I'm going to pull m up, and m, if you remember, that's granularity of our grid, right? So I'll say m power d. Why am I saying d? Well, because I'm going to generalize our formula soon. So d is 2. In this case, we have weight and height. And then delta V is a volume of the cell, and in this case it's a square, not square, but it's like a rectangle, right? It's two-dimensional, so it's just weight and height. But it's, see, I removed this m. It used to be under. It was the cell, but now the volume is not of a cell, but entire domain, right? So it's going to be from 140 to 200 and from 40 to 120. Now think about this approximately, right? So when we're multiplying the density by entire area or volume, we should get something close to 1, right? And that's what I'm going to do. I'm going to remove this. So my formula further simplifies, and I'm going to say that the precision or uncertainty, noise, whatever you call it, of my estimate of the probability is now this number, right? So it's m power d 2 and so on. So when I'm increasing the sample size, my precision is increasing. Well, we expect that. But we also know that when I'm increasing the granularity of my grid, my error is increasing. And we said, right, that when we went from 2 by 2 to 8 by 8 matrix, there were fewer observations in each cell. Let's take a look at them, right? Fewer. Okay, this was 2 by 2. Let's make it 8 by 8 here. You see the number of observations in cells are smaller now, right? So we know that, and that increases the error. But what we didn't pay attention before was this dimensionality, and we're going to look at what's the implication. The implication is the following. Suppose we want certain error. Maybe we want 1% error, no more than 1%. What should be my sample size, right, at a certain granularity of my grid? So that's the formula we will use, right? So our sample size n is going to be, it's proportional to the granularity. If granularity is bigger, we need a bigger sample, right? If error is smaller, required error is, if we want a very small error, again, that increases the number of observations. But how? Look at this. So imagine we have a grid 10 by 10, not that granular of a grid, 10 by 10, it's not that that many details, but let's imagine there's 10 dimensions. Easy, right? So we were talking about height and weight, but with human biometrics we saw there was 20 columns. It could be 20, but let's think of 10. So we have 10 by 10 grid, and we have 10 not 10 by 10, but 10 by 10 by 10, and so on, right? So we have 10 variables, each one has 10 cells, right? And we want 1% error. If you plug these numbers, you'll get n required 10 power 14. There isn't that many people on Earth, right? So, wow, what happened? It happened that when we increased, the main thing came from, the main effect came from the dimensionality. Why am I saying so? Look at this. If the dimensionality was just 1, if we were just interested in the height and we wanted maybe 1% precision, we would need only 1,000 people. It's doable, right? It's a lot of people, but it's doable. These guys, they got 507. But if I just increase the number of variables, I'm having still the same grid, 10, 10 cells by each axis, but now I have 10 variables. All of a sudden, look at what's going to happen, right? The number of the size explodes. The sample size requirement explodes, and that's in not in statistics, but I think in like machine learning or in statistics too. This phenomenon is called dimensionality curves. When you are increasing the number of dimensions, which is very easy, you saw in options pricing or options risk management example in the very first video of this triplet. It's easy to imagine. Just look at the strikes of an option. There could be 30, 40 of them, and so on. So dimensionality increases very quickly in statistics, especially in machine learning. But in any field like economics and finance, you are rarely interested in just one variable. You want several. And when you're estimating the joint distribution, the point I want you to sort of take from this whole triple video introduction, right, is that joint distributions are very difficult to estimate. They're very difficult to estimate, and the estimation methodology which I used here through frequencies, it sounds kind of simplistic. Obviously in the industry there are all kinds of methods of estimating the PDFs, and no one will do, well, in some fields they actually do something like this, but let's say in finance you probably wouldn't be doing this. You would be doing parametric estimation and so on. You can use all these fancy techniques, but in the end, what is the basis of all these techniques? The data, and the data is here, so it's hard to dance away too far from the richness of your data. And what we're saying here is the following. What I'm trying to say here is the following. If you have a joint distribution, when you add more and more variables in your joint distribution, when you're interested in more than one or two variables, it becomes very difficult to estimate the joint distribution with any kind of respectable precision. So that's your dimensionality course. It's very difficult to estimate joint distributions. Very difficult. And what copulas do, right? Let's get back to beginning of the video one. Let's link it back. What copulas do, they promise. They give you this promise that you know what, you to estimate the joint distributions, which is very difficult, we just found, you only, if you are using copulas, then you only need to estimate marginal, like one-dimensional distributions, which we found are easy, and then you can combine them into joint. So you can calculate with, let's say, 1% precision those 10 variables, each one of them separately with high precision, and then using copula, get the joint distribution, hopefully with about the same precision. So you solve or cheat yourself out of these dimensionality curves. That's what copulas are promising.